In this video, I'm going to go over AP Precalculus topic 3.7, which is about sinusoidal data modeling. So there's a lot of different real-life scenarios that can be modeled by our sine and cosine graphs. There's just a lot of things that are cyclic or periodic that we can use an equation of sine or cosine to describe them, to model them. So before we get into those examples, I want to review a few quick things. First, the parent graphs for sine and cosine, because this is going to help us with identifying whether we might want to use a sine or a cosine, or when we're writing the equations, if we need to apply some phase shifts and what those are going to look like. So sine starts at the midline and oscillates between 1 and -1. Okay, so it sort of starts, which is sort of a bad term because this does go on repeated forever, but when it crosses the y-axis, it starts at the midline and moves up, versus cosine starts at the maximum, but it still oscillates between 1 and -1. Okay, and then if I have a negative, those are just going to be opposite. So if I have a negative sine, it's going to start at the midline and go down. Cosine is going to start at the minimum value if we have a negative in front of it. Okay, and then we have the general equations. So whether it's sine or cosine, we have A sine or cosine B, and then in parentheses x plus C plus D. So these are the same transformations that we've seen back in Unit 1, specifically 112. The value of A, the absolute value of that, is going to give us our amplitude. The period is going to come from B. The period is going to be 2 pi divided by whatever that value is, because the period for sine is 2 pi, and then our horizontal dilation is the reciprocal of B. But if you remember 2 pi over B, you're in business. Our vertical shift is going to be whatever our value of D is. So if D is a positive, the graph's going to move up. If it's negative, it's going to move it down. This is also our midline. Okay, is going to be y equals D. And then our horizontal translation is going to come from our value of C. In our general formula, if this is plus C, our phase shift is negative C. Because if this is positive, our graph is going to be moving to the left. If this is negative, our graph is going to be moving to the right. So let's look at our first scenario. In predator-prey situations, the number of animals in each category tends to vary periodically. A certain region has pumas as predators and deer as prey. The number of pumas varies with the time according to the function 500 plus 200 sine 0.4t minus 0.8. The number of deer varies according to the function d equals 1500 plus 400 sine 0.4t. What we're going to use this for is to determine the maximum and minimum number of deer and the maximum and minimum number of pumas. Okay. The two key pieces of information that we're going to need here are the vertical shift and the amplitude. Okay, so my vertical shift, it's written in the front, but we're still just adding 1500. That's my midline. Okay, the amplitude is 400, which means I'm going to go 400 above that up to 1900, and I'm going to go 400 below that down to 1100. So for my maximum, we're at 1900. For the minimum, we're at 1100. I can repeat that for the pumas. So my maximum here is going to be my midline, which is 500, plus my amplitude. My minimum is going to be my midline minus whatever that amplitude is. All right, the average high temperature per month for Colorado Springs can be modeled by a sinusoidal function. The minimum high temperature of 43 degrees occurs in January, which we're going to call T equals 1. The maximum high temperature of 85 degrees occurs in July, which is T equals 7. We're going to write an equation in the form f of t equals a cosine b t plus c plus d, which gives the average high temperatures for each month. So what I like to do is draw myself a little picture. Okay, and I have 2 points. I have my temperature in month 1, my temperature in month 7. My temperature in month 1 was 43, and my temperature in month 7 is 85 degrees. So if I were to graph this, we have our minimum here, our maximum here, which gives me half of a sine or a cosine curve. This one's going to be a cosine, so we're going to approach it that way. Okay, we need to find the variables for the values for A, B, C, and D. The A is going to come from our amplitude. So the amplitude for this, well, let's think about this. Okay, the distance from here to here is going to be double the amplitude. So if I subtract 85 minus 43 and divide that by 2, so 85 minus 43 is going to be 42. Divided by 2 is an amplitude of 21. The distance from here to here is 21. The distance from here to here is 21. My B is going to come from my period, and you can find these in any order. Oh, sorry. So A is going to be 21. Now we might end up making that a negative, and I'm going to discuss that here in a second. My period is how long it takes to complete a 1 cycle. So it's going to go from a minimum to a maximum back to a minimum. My next minimum is going to occur at 13 because our period is 12 months. So my B is going to be 2 pi divided by 12, which reduces to pi over 6. Okay, I'm going to come back to the phase shift. My vertical shift, or my midline, is going to be, there's a couple ways you can find this. I have the amplitude, so I can take the amplitude and add it to my minimum or subtract it from my maximum, or I can find the average of these two numbers. We'll get the same value either way. So if I add those together, we're going to get 128 divided by 2 is 64. Okay, finally, my phase shift. Okay, we have options here. Okay, we want to write this as a cosine, which starts at the maximum, but we can make the A negative, which would make it a negative cosine, and start at the minimum. Either way. So option 1 is to do a phase shift of 1 with a negative cosine graph, or a phase shift of 7 with a positive cosine graph. I'm going to go ahead with 7. Okay, which means my C is going to be negative 7. Since I'm choosing a positive cosine, my A will remain 21. So putting all this together, we have a positive 21 cosine. My B value is pi over 6. My phase shift of 7 means my C value is negative 7, plus our vertical shift of 64. Alternatively, if I had chosen a negative cosine, this is negative 21, and then that phase shift, that horizontal translation, would be given by a -1 on the inside. Okay, sound waves are another thing that are cyclic. So a piano tuner strikes a tuning fork for the note middle C. It creates a sound wave that can be modeled by y equals 1.5 sine 524 pi t, where t is in minutes. So what is the period of our function? Our period is always equal to 2 pi divided by our b value. Okay, which, if I simplify this, is 1 over 262. So that means to complete one cycle occurs in 262 seconds. Okay, the frequency is always the reciprocal of period. So if my period is 1 over 262, my frequency is equal to 262. Okay, so this here is seconds per cycle. So if I have the reciprocal, that's cycles per second. And this has its own units called hertz. Okay, so a tuning fork for middle C has a frequency of 262 hertz. That's the pitch that you hear. Next, and this is going to be similar to our scenario above, where we're going to be given 2 points. So we're going to do another cosine curve. We're going to find the constants a, b, the points 3, 10, and 6, -4 represent a maximum and a minimum respectively. What are the values of a and d? And I'm going to draw myself a picture. And how detailed you make this is up to you, and if you can do it without the picture, good for you. So we've got 3 and 6, and then I have a maximum at 310 and a minimum at 6, -4. Okay, and we don't need to find all our values, A, B, C, and D. We just care about A and D from our amplitude and our vertical shift, or our new midline. Okay. My amplitude is going to be half the distance between the max and the min. So if my max is at 10 and my minimum is at -4, then my amplitude is going to be half of that gap, which is 14. So my A is going to be 7. Then I can either take that 7, subtract it from 10, or add it to -4, or take the average of the max and the min. All of those will get us the right answer. So if I average 10 and -4, we'd add those and divide by 2, which is going to be 6 divided by 2, which is 3. Or, like I said, take 7, subtract 7, we get 3. If I take -4 and add 7, we get 3. Either way, my D value is 3. Okay, our next scenario is where we're counting the minutes of daylight per month. So we have the first of each month converted to a day number from 0 to 365, I guess 1 to 365, and then the number of minutes of daylight. So you'll notice in my table here, we start at 800, it goes down to 600 or so, and then it goes back up. So this is a southern hemisphere city. So this gives the amount of daylight in minutes for various days of the year for a city in Brazil. We're going to use the calculator to come up with a sinusoidal regression for this. So first we need to enter our data. Okay, so we're going to go to Stat, Edit. Okay, if there's something in here, you can highlight the list and do clear, or you can just overwrite the numbers, but I find I like to have a clean slate. Then you want to enter the day numbers in our list 1 and our number of daylight minutes in list 2. Okay, now that I have this, we're going to run our sinusoidal regression. So we go to the Stat menu again. Now we're going to go over to our calc. All of our regressions live in this list. We've done many of these. The one we're doing today is the sine regression. We're going to do the default's 3 iterations. We want to do list 1 and list 2, and typically we want to store this equation. If you use your shortcut F4 menu, we can store it in Y1, and then we will calculate. Just like all of our regressions, we're given the general equation, and then we're given the values that we're going to plug into those. This b is an unfactored form. So the b that we have here, we'd have to do a little bit of work to get, it'll give us our, so we're just going to fill in these values. I'm going to go ahead and round to 3 decimal places. So plugging in those values, this is the general equation for our sinusoidal regression. In my last example, this is going to model one of our free responses. So free response 3 is always going to be a sinusoidal function modeling some sort of real life scenario. The steps are going to be the same every time. The context will look different. So here, the blades of a ceiling fan rotate at a rate of 4 rotations per second. Point A is located at the tip of one of the blades, which is 1 foot from the center of the fan. The center of the fan is located 6 feet away from the wall that we have shown here. At t equals 0, point A is at the farthest distance from the wall. The sinusoidal function models the distance between A and the wall. So we're going to write a model H that models the distance between point A and the wall as a function of time. So let's add a few pieces here. The farthest distance is going to be 7 feet away. When it's closest, it's going to be 5 feet away since our blades are 1 foot long. So I'm going to transfer this information to our graph. We are no strangers to this setup. This will always be there. There's no axes presented, but we're going to find possible coordinates for F, G, J, K, and P. Okay, I'm going to first label these 3. My max is going to be at 7, my min is at 5, and my midline is going to be at 6. Okay, this one says that the first maximum, our 6, occurs at t equals 0. So my coordinates for this are 0, and it takes it rotates at a rate of 4 rotations per second. So we'd see 4 of these per second, which means our next maximum is going to occur at 1/4. Okay, if our maximum occurs at 1/4 and 0, our minimum is going to occur halfway in between those at 1/8, which means it's going to cross the midline here at half of that, which is 1/16. So this distance is 1/16. So all of these distances are 1/16 between points. So we have 1/16, 2/16, 3/16, 4/16. So my points from all of this, my F is 0, 7. G is 1/16, 6. My J is 1/8, 5. K is 3/16, 6. And our P is 1/4 back up at 7. The second part, and this will always be the same, is we're going to write a function for this. The only thing that may change is this might be a cosine or a sine. In this case, we're going to attempt a sine curve. So from my graph here, I need to find my A, B, C, and D. Okay, so I'm going to start with A. My amplitude for this graph, the distance from the midline to the top or the midline to the bottom, is going to be 1, which means my A is going to be 1, potentially -1, depending on whether we want to do a positive sign or a negative sign. My period is how long it takes to complete one cycle, which we said was 1/4. So my value for B is going to be 2 pi divided by 1/4, which will be 8 pi. I'm going to come back to the phase shift as last. My midline is y equals 6, which means my value for D is going to be 6. And then finally for my phase shift, we have options, just like we saw before. If we're doing a sine, that means we're starting at the midline. So I have 2 points that I could use for that, either G or K. If I use G, I'm going to have a negative sign because it would start down and then back up. If I use my start value of K, which is what I'm going to choose, we're going to have a positive sign. So my phase shift is going to be 3/16, which means my C is a negative 3/16 in my equation. Now here we found the constants. I'm going to go ahead and put it back in our formula though. So this will be a positive 1 sine 8 pi t minus 3/16 plus 6. So again, that 3/16, if I were asked to do a cosine, we'd be in business. We'd just start without a phase shift. But since it's a sine, we need to have a phase shift. A positive sign starts, quote unquote, at a midline moving up. So that's why my phase shift is minus 3/16. The last part of this question, again, is always the same. Save which interval we're looking at. So here we're looking at the t coordinate of j is t1 and k is t2. Okay, and we're going to be asked the same things for this every time. On this, is h positive, negative, is it increasing or decreasing? Okay, these values are positive, which means we're positive, and this graph is obviously increasing on the selected interval. The last part of the question says, describe how the rate of change is changing. We are looking at the concavity. Here is concave up. So since our graph is concave up on T1, T2, we want to say what interval, because our graph is not always concave up, but on the interval in question, it is. Then the rate of change of h is increasing. And we only have two options there. And it might be increasing on T1, T2. Be real specific. Okay. The only thing that would change is if the graph was concave down, this would be decreasing, but we're going to use that same terminology. So this was topic 3.7 on how we can use sinusoidal models to model real-life situations.